Hi, so we'll go over a few topics in ACE-TAM, primarily the first couple in severity and aggregate models. And we'll go over like the crux of the some of the core concepts. The first one is on mixtures. Now, what is a mixture? You can think of a mixture as a distribution that is conditioned on a parameter that follows another distribution. And so you can use the law of total expectation to get the unconditional expectation. And then you can use the law of total variance to get the unconditional variance. So we have x given some lambda. That lambda follows the distribution. And so if we want to get the probability unconditional x is greater than 2, for example, then we need to take the expected value across all values of lambda, right? So lambda could be anything, right? That is, lambda could be anything. To account for those probabilities, that's why we take the expected value of whatever probability of x greater than 2 is, right? So what it is really is expected value of the probability of x greater than 2 given lambda. And then you take the expected value of that across all of the lambdas. So you can think of this as a probability multiplied by the probability lambda is a certain value, right? And then you integrate that, and that is your expected unconditional value, right, of the probability x is greater than 2. So that is mixture. Law of total expectation, the law of total variance, expectation of a probability of unconditional x greater than some value, right? So these are the things you need to know for mixtures. For frailty models, these are hazard functions that are conditioned on a random variable, right? So in this case, we have a random variable, right, times a of x, and this random variable follows some distribution. So it is a hazard function that is conditioned on a parameter which is a random variable. Key formulas here: survival function is e to the negative h of x, and then s of x survival function is the MGF of that random variable evaluated at negative a of x. And similar rules for unconditional expectation apply here as well. So if you want the unconditional survival, right, that will be expected value of your conditional survival. And then same thing for h of x, that will be your expected value of your conditional h of x, right? Tail weight is known to be as how much probability or how little or how much probability do we give to large extreme losses. There's 4 ways to identify tail weight or to compare different tail weights across different distributions. We have number of positive raw moments, so the greater number of positive, the fewer the positive raw moments, the greater the tail weight. Ratio of s of x or f of x, right, as x approaches infinity. If it approaches infinity, that distribution in the numerator has a greater tail. Hazard function and mean excess loss function. So hazard function, right, we know is f of x over s of x, right? Right. If this increases as x decreases, we know it has a heavy tail. Inverse is true for mean excess loss. Yeah, as d increases, if mean excess loss increases, we know it has a heavy tail. Now, how do we model maximums of blocks? How do we model maximums of blocks? So say you have a certain distribution. You sample different blocks. Let's say you sample 5 blocks. You select the maximum of those blocks. How do we model that? How do we model the maximum of the blocks? And as n approaches infinity, as the number of observations in a certain block approaches infinity, that's the max of the population. So how can we model these block maximum? we can model those through what we call h of x. Right? H of x is our distribution. And so by the Fisher-Tippett-Gnedenko theorem, if they follow this distribution, so if they follow this, if the limit as n approaches infinity, n times the survival function or the max function, right? If you can get it into this cumulative density function, h of x, right? Also known as the generalized extreme value distribution, then we know that they are in the maximum distribution of attraction of h, right? Which is the GEV, or the generalized extreme value distribution. So again, how to think about this is you can think about you have different blocks. So let's say you have 50, 10, 10, 20, 30 blocks. You're selecting the max out of each block, right? And those maximums follow a certain distribution, right? And that distribution is GEV. So max of any block can follow any possible value, can be any possible value. We model that through GEV. Now there's three types: Gumbel, Frechet, and Weibull EV. Gumbel when e equals 0, greater than 0 and less than 0 for Frechet and Weibull extreme value. These are your parameters, right? Alpha and tau. And then we have a trade-off between block size and the number of blocks. If your block size is large, you're more likely to have the maxima in the tail, like the maximum value of the population. The maxima is going to be in the tail more often if you have a large block size. But what that means is if you have a large block size is you have fewer blocks. So you have fewer data points to make your estimates, parameter estimates. So there is a trade-off between block size and number of blocks, between having accurate estimation, more data points for your parameter estimations versus making sure that your maxima is actually in the tail. Right? If you have a large block, it's more likely that the maxima is in that block. So we talked about maxima of a block, right? Maxima of a block. Now, if we extend that to excess loss, it's almost similar concept in that we're modeling tails, right? We have x minus d given x is greater than d, right? That's your excess loss. And now by the, I forget the theorem name, but if it follows a GEV distribution, right? So if x is in the MDA of h, if it follows GEV distribution, if the block maxima follows GEV distribution, right? Then by this theorem, we also know that the excess loss also follows a certain distribution, right? Okay, so we're going to continue on some of these topics. So one thing I wanted to mention so we talked about Frechet, Gumbel, Weibull, extreme value. So it's called the Pickens-Belcamp-de-Haan theorem, which states that if you know that the block maxima follows the GEV distribution, the excess loss distribution follows the GPD as the threshold D approaches the maximum loss. So if you know that the block maxima follows GEV, by this theorem, you already know that the excess loss follows this GPD generalized Pareto distribution. And so we have Gumbel, Frechet, Weibull extreme value for the block maxima distribution. And from those, we have Pareto, exponential, and beta for the GPD for the generalized Pareto distributions. And now one important thing to know about Frechet, is that for Frechet, there is a way to actually approximate the tail index. So if you have Frechet, the way you can model the survival function is S of x equals x to the negative alpha, and that alpha is the tail index, right? That alpha is the tail index times L of x. And then that L of x is what we call to be slowly varying at infinity, which just means that the limit as x approaches 0 of LT of x, where t is any integer, x over L of x equals 1. Right? We have a way to approximate this tail index through this empirical data. Right? And so that's how we can, that is what we call the Hill estimator. This is what we call the Hill estimator. Right? So what you do is you take the natural log of all of the values that are above that threshold, right? Xj, right? Divide by n minus j plus 1, and then subtract by the natural log of xj. And then similarly, we can approximate S of x, or the survival function, as well. So the probability that a certain value is greater than x. And one of the benefits of this is because of this, we're able to bypass the beta parameter in Prechet, or in Pareto. So that's useful there. Just go over a couple more concepts. So MLE, maximum likelihood estimation. What are we doing? We are maximizing the log likelihood of observing these data points, right? So for what theta value, for what alpha value, it makes this data that we've observed most likely to occur, right? And so you take your product of the data points, right? Take the natural log, take the derivative of that, set equal to 0. That is how you're going to maximize the log likelihood. And then sometimes you can actually get an exact moment matching if you want to get the variance. So if you want to get the variance of, let's say, theta, and if theta follows a Poisson, right? If theta follows a Poisson, you know that the ML, you know that it's what is the variance of x bar, right? Right? Because you know theta hat is equal to x bar for Poisson, right? And so you're able to do that. So sometimes you can do those, you can exact moment matching, but other times where there is not an exact moment match, then you have to use Fisher information, which allows you to get the asymptotic variance. So that is through these formulas here. And then another concept is delta approximation. So if Fisher information is you want to get the variance of the parameter, right? But what if you want to get a variance of a function of the parameter? Then that is when you use delta approximation, which is this right over here. And then for the two parameter case, you extend it out to something like this. Okay, and again, it's a function of the parameter. So it could be the mean, it could be the median, it could be the 90th percentile. As long as it is a function of the parameter, right, you can take the variance of it and you can use delta approximation. That's the thing. As long as it's a function of the parameter. And then now just some clarifying concepts on Buhlmann and Buhlmann-Straub. So Buhlmann is we have empirical data, we have theoretical data, right? We have empirical and we have theoretical. Right? What are the assumptions of Buhlmann? Condition on theta, losses in each period x1 to xn are independent IID with mu, right? With mean mu. Right? So by losses in each period, you can think of this as, again, this is uniform exposures. So we're observing, let's say, one policyholder for 3 years, right? One policyholder for 3 years, and that is what we're observing. Losses in each period are IID with the same mean, right? So the losses in period 1 for that policyholder, right, have a certain mean. They have the same mean in the second year, same mean in the third year, right, for that same policyholder. And with the same variance as well, right? So in year 1, right, policyholder can experience any amount of loss, right? That expected value and variance is the same across all periods, right? That is Buhlmann. Then Buhlmann-Straub is conditioned on theta, your average losses in each period, right? So there is no longer just one exposure, right? You don't have just one exposure. It's multiple of these different exposures that you have, right? So instead of just one policyholder, you have 2, 4, and 2 in this case, right? So it's multiple policyholders, right? Multiple exposures. That is why we call it non-uniform exposures, right? Because you're not just observing, you're not observing one policyholder, right? It's multiple policyholders, it's a multitude of exposures. Right? And so those in each period, the average losses in each period. So what you're going to do is you're going to divide the number of losses or the number of claims, right, in each period by the number of policyholders. That is your average, right? Those average losses in each period have the same mean. Right? So that is why we refer to this as expected value of xj, right? xj, right? Where j refers to period j, right? And mj refers to the number of exposures in period j. right? So again, Buhlmann, we have uniform exposures, right? Same number of policyholders that we're observing, right? And those follow a same consistent mean and variance. Bowman-Straub, we have non-uniform exposures, right? We have non-uniform exposures, and the average loss in each period follow the same expected EV and variance, right? EV and then variance you actually divide by the number of exposures in that period. So that is a way that is the distinguishing factor between Bowman and Bowman-Straub. And then another concept is when we have mu, v, and a. So mu, v, and a are expected hypothetical mean, right? Variance of expected process variance, right? So we have expected hypothetical mean, process variance, and variance of hypothetical mean, right? The interpretations of these are different. So we're going to go through these. So mu, right? Expected unconditional E of x is E of x, right? What is the expected value of x? And what's the expected value of unconditional expected value of x? Right? Process variance is how much do the losses in each period vary? So then this is important to understand. Right? How much do the losses in each period vary? So period 1, we have x1 to xn1. Period 2, we have x1 to xn2. How much do those vary? Right? And then you average those across all the different values of theta that you can have. That is your expected process variance. How much for a given theta, right? For a given theta, how much do those losses vary? And then you are averaging those across all possible thetas. That is your expected process variance. When you go to the variance of the hypothetical mean, right? So this is a good way to visualize it, right? You have your thetas, and then you have for each theta, you have x1 to xn, right? Variance of hypothetical mean is how much do the expected losses vary across all the thetas, right? How much do the expected losses vary across all the thetas? And then if you want, and then to get that all into one credibility factor to assess how much do we want to weight these empirical data points, that is our k, and then we use k when we calculate our actual credibility factor to weight our empirical data. So these two quantities are to measure how much credibility or reliability we can have on the observed data points. So at a high level, those are the concepts I wanted to cover. Now we can go over some NFL predictions. Okay, so we went, I believe, not the best first 2 weeks, 3-7. So we have right Casey 5.5, Ravens 5.5, Bears 1.5, Pittsburgh 1.5, and Chargers 2.5. Sort of the trend I'm going with now is more what conference upsets occur the previous week and then not having those upsets the following week. So that is the rationale behind the Steelers and Chargers pick. AFC upsets twice week in a row are rare, and then consecutive SNF upsets are rare. So that's Chiefs 5.5, and Ravens Lamar versus NFC opponents, and then the one of the trends that actually didn't follow through last week, which was if if you lose by more than 20 points, or you fail to cover by more than 20 points, and you're coming back as a favorite, I believe that has covered 70%. Right, so that is the logic behind Bears 1.5. They're at home too as well. So KC 1.5, Baltimore 5.5, or KC 5.5, Baltimore 5.5, Bears 1.5, Chicago 1.5, Pittsburgh 1.5. and then Los Angeles Chargers 2.5. Hopefully we can get back to 500 at least with these picks. I feel good about Pittsburgh. I feel good about these three. I'm a bit concerned with the points for these. Hopefully we can get back on to at least 500. So that's all for this video. See you in the next video.